you need a lot of stamina because we have 3 talks without a break. Because I thought it's better to, get done and people can go to the airport wherever you need to go, and then the workshop ends. Okay? So 3 45-minute talks. Okay, and today we get the second talk of Soheil, which I'm very much looking forward to after the exciting first talk. Thank you.
Thanks, Monica. And good morning, everybody. So this is the second part of my talk. I'll continue to talk about recent progress on sublinear time algorithms for maximum matching. And what I'll be talking about today is based on joint works with Mohammad Roghani, who is sitting here, and Aviad Rubinstein. In the first part of the talk, I talked about sublinear algorithms more on the algorithmic side. I talked especially about how sublinear algorithms have helped design much faster dynamic algorithms for maximum matching, which is basically why I decided to talk about sublinear algorithms in this workshop. Today, I'll only talk about lower bounds. There have been some exciting developments on proving lower bounds for this problem that I'm planning to cover today. Okay, if you missed the first talk, it's completely okay. I'll give all the needed definitions. Or if you attended the first talk and forgot about everything, it's okay too. Okay, so I'll start by defining the problem, which is the maximum matching problem. A matching is a collection of vertex disjoint edges. And we want a matching that's as large as possible. That would be the maximum matching problem. An approximate matching is a matching that's approximately as large as the maximum match. The problem has numerous applications. I won't talk about them. Okay, so when we talk about sublinear algorithms, we want to specify how we can access the input. It's very important how the input is represented. If we only want to see a small fraction of the input and decide on the output. 2 models are common: adjacency lists and adjacency matrix. In the adjacency list, you can query, you specify a vertex, an index in the list, and in return, you get the ID of that neighbor. Adjacency matrix, you specify 2 vertices, and you're given if they are adjacent or not. Okay, trivial bounds. You can query everything here. It takes order m queries, and you can solve it using your favorite linear time approximate matching algorithm. In the adjacency matrix model, you can query every entry, and it takes n squared time. Oh, and throughout the talk, n will denote the number of vertices, m will denote the number of edges. So I mentioned this also in the first talk. These trivial bounds are actually optimal if you want to find the edge set of the matching, and even if it's just an approximate matching with very bad constant approximation. So kind of the right question, in a sense, for sublinear time algorithms is, can we estimate the size of the maximum matching instead of reporting all of its edges? And today, I'll specifically focus on adjacency lists. This is the setting we will prove the lower bounds in. In other words, we will say that any algorithm, for example, providing an alpha approximation, has to query this amount of entries of the adjacency lists. Okay. Any questions about the model? All right. Okay. So I just quickly want to again repeat what algorithms are known. I mentioned this in the first talk as well, but just to give you a sense in case you missed the first talk. So basically, what we know right now after a long line of work is these 3 algorithms. One can get a half approximation. This is the approximation. This is the running time. One can get a half approximation in order n time and polylog n time, hiding all polylog factors. So one can get half approximation of the size of maximum matching in order n time. You can get slightly better than half and slightly worse than n time. This was a joint work with Aviad, Mohammad, and Amin. And in a nice result this past Fox, Cheyenne Peter and Tachapon showed that you can get, in subquadratic time, a 1 minus epsilon approximation. All right. So this is the state of affairs for this problem on the algorithmic side. And today, we will talk about lower bounds. Okay? And just, I wanted to quickly talk about the motivation via dynamic matching. So basically, in the dynamic matching problem, you want to maintain a large matching or an approximation to the size of the matching as the graph changes. So there's been a whole series of trade-offs for this problem, which seemed a bit tricky to improve upon. But since last year, there have been a lot of improvements over these. And all of these blue improvements basically use sublinear algorithms. But one crucial difference that these blue results all only maintain the size of the matching, whereas the previous bounds, previous algorithms maintain the matching itself. Okay, so the sublinear time algorithms for maximum matching have a lot of implications in the dynamic setting. So we want to study sublinear time algorithms, and also we want to study what they cannot do. So that's why we'll talk about lower bounds today. So I start by talking again about the lower bound construction of Parnassian run, probably in a little bit more detail, because we'll also use some of the ideas in the new lower bounds. So, so what is the Parnassian run lower bound? It says that if one wants to provide any constant approximation of the size of the matching, even if the matching is guaranteed to be of size linear in n, one has to spend omega n time. One has to query omega n entries of the adjacency lists. And the construction is as follows. So we have epsilon n dummy vertices. So this is the yes case. This is the no case. We're going to have to distinguish them if we want to provide a constant approximation. So in both types of graphs, we'll have epsilon n dummy vertices. And we will also have dummy vertices in our construction. So it's important to know what role they're playing. So these epsilon n dummy vertices, because there are only epsilon n of them, they're not going to change the size of the matching by much, by more than epsilon n, right? But on the other hand, they can have epsilon n squared edges adjacent to them. So they make the graph super dense, and at the same time, don't really change the size of the matching. OK, and then we have a core connected to these dummy vertices. So the core, in one case, includes a perfect matching, the red matching. And the core in the second case does not have a large matching, right? So in this graph, the matching is very small, has size epsilon n. You can only match the dummy vertices. Here, you're going to have a large matching. And if you want to provide a constant approximation, constant better than epsilon, you're going to have to distinguish these two. And why is it intuitively hard to do this with less than n queries? So what's the natural algorithm? You pick one vertex. You go over the edges to see if there's another non-dummy neighbor or not. So that's going to take omega n time. Yeah, so one caveat is that here you can actually quickly, in the adjacency list model, you can quickly, in log n time, figure out the degree of a vertex. So here you can quickly say that these vertices have degree that's smaller by 1 than the vertices here. So you can actually distinguish these two graphs pretty fast. But this is easy to fix. You just add 2 stars. All the vertices will have the same degrees in the two graphs, except for these 2 vertices. And because there's just 2 vertices, finding one of them also requires querying omega n vertices. So this is the whole lower bound. That proves any constant approximation, omega n time for it is needed. OK, so essentially, this proof, what it does is that every vertex, it says that every vertex has just one important edge and has a large linear in n degree. Just to see at least one important edge of just one vertex, you're going to have to spend omega n time. So that's the sense of the lower bound. So what I'll talk about now is proving superlinear in a lower bound. So we want n to 1 plus epsilon. Yeah.
What is the degree of a vertex before or after you added the star?
So before I added the star, these vertices would have degree epsilon n only to the dummy vertices. And these would have epsilon n plus 1.
The reason I ask is because you can basically detect the roots of those stars, but it will take you epsilon n time.
Yeah, it will take omega n time, exactly. So long as epsilon is constant. Right. OK, great question. yeah, so we want to prove superlinearity and lower bounds. And the problem with superlinearity and lower bounds is that you cannot just have one important edge per vertex that you cannot discover, because you can just pick one vertex, maybe at random, just query all of its edges. That takes order n time. So you will see some important edges, but the construction should basically say that even though you will see these important edges, you cannot figure out that they're important. So that's going to be the what we'll have to do. Okay, so what do we get? So this is a theorem we proved with Mohammad and Aviad at this past stock. So we showed that for any fixed positive epsilon, any better than 2/3 approximation of the size of the maximum matching in the adjacent to this model requires n to the 1.2 time. So this is superlinear in n. So just put together the lower bounds and the upper bounds. So these were the upper bounds that we knew. The Parnas-Run lower bound basically rules out any better than n time algorithm for any constant approximation. Here we rule out algorithms in this region. We basically said that any better than 2/3 approximation would have to spend more than n to the 1.2 time. Okay. And as you see, there are a lot of regions where the answer is unsure. For example, can we get all the way up to 2/3 in order n time? There are a lot of nice open questions to think about. Okay. Any questions about the statement of the result? Okay.
Are you going to go into more detail on this?
Oh, yeah. So this is what I spend most of the talk on. Right. Okay. So I start by defining the input distribution. What is the distribution of the graph that is hard to provide a better than 2/3 approximation on? So this is going to be the construction. So we will still have epsilon and dummy vertices. They played exactly the same role. We want to make the graph dense, and we do not want to change its matching. So these dummy vertices do exactly that. And then this is what happens in the core. This is now more complicated than just having either a matching or nothing. Okay. So what's going on here? We have three types of vertices: the S vertices, the B vertices, and the A vertices. Okay. And in case it's not clear, there's also a graph of degree D between A and B, and a graph of D between A and B here. Okay. So what's this distribution like? So we have, again, two types of graphs: graphs on which the matching is large, graphs on which the matching is small, and any better than 2/3 approximation should distinguish the two. So this is the no case where the matching is small. So what is it like? So we have a matching from the S vertices to B vertices. And when you look at the core, the degrees of the vertices in S is always going to be 1. And the reason we chose S is because we call them singleton vertices. So singleton vertices only have degree 1. And they have to be in the matching. So it's generally, you can prove that if you want to find the maximum matching, any degree 1 vertex, you're just going to have to match it to its neighbor without loss of generality. Okay, so these degree 1 vertices will be adjacent to B through a matching and have degree 1 in the core. They're still connected to the dummy vertices. Okay, and then the A vertices are only adjacent to B. So if you look at the matching of the core, if you match S to B, the A vertices will be left unmatched. So the core, the optimal matching in the core is just matching S vertices to B vertices and leaving all the A vertices unmatched. And now in the yes case, what I'm going to do is I'm going to add a matching between the A vertices. So one case, the matching is 1.5 times the matching in the no case. And any better than 2/3 approximation should be able to distinguish the two distributions.
Are A and B the same size?
A and B for not supposed that they're of the same size. So just one comment. This is a wrong distribution, but it provides the right intuition about our final distribution. So we're going to have to change something slightly, and that's exactly the size of A and B. And yeah, but for now, suppose that A and B are of the same size.
One basic question in this picture: why you need these dummy T vertices again?
So, okay, I'll answer you in a minute. So the answer is the following. so first of all, before telling you that, I'm gonna, once I construct this graph, I'm gonna assign random IDs to the vertices, right? So I want to basically hide which of these sets a vertex belongs to. But actually, I'll give away vertices in T and vertices in S. So I'm gonna tell you these vertices are in S. These vertices are the dummy vertices. What I'm not gonna tell you is the vertices in the union of A and B. I'm not gonna tell you if they're A or B. So you're gonna have to figure that out yourself. Okay. So now suppose that you take one vertex in either A or B and you want to verify whether it's in A or B. So what's a naive algorithm? You want to have to basically go through the neighbors and see if it has a neighbor in S or not. That's the only difference between A and B. Okay. So what do? You go over the neighbors in the adjacency list of that vertex until hitting an S vertex. And I've given you for free the S vertices. So once you see an S vertex, you're done. You know that that is an S vertex. So you can spend omega epsilon n time, because all the degrees are still epsilon n at least, because of the dummy vertices. So once you go through the adjacency list, it takes epsilon n queries to actually hit that S vertex. And in case I forgot to mention, I'm also going to randomly permute the adjacency lists.
Everyone is connected to the dummy, or?
All vertices in the core will always be adjacent to all vertices, all dummy vertices.
So then it's not a bipartite graph anymore.
You can make it bipartite easily. It just, the picture would be a little bit
Okay.
more complicated. But yeah, but you can easily just, yeah, the statement holds also for bipartite graphs. Good point. Okay. Yeah, so naively, if you want to basically check if a vertex is an A vertex or a B vertex, you're going to have to spend omega n time. But that's not going to be enough to distinguish yes and no. We're going to actually have to figure out if there are any AA edges. So the difference between yes and no, remember that there was inclusion of this AA matching. So we're going to have to basically check if there is an AA matching in the graph or not. Okay. So what's a naive algorithm? So the naive algorithm is I start with a vertex in A. I can find one in order n time. I just pick a random vertex from A union B with probability half is in A. In order n time, I check this. If it's not, I sample again. So that's easy. So I start with the vertex in A. And then I go over all of its neighbors. Some of the neighbors go to the dummy set. I ignore those. So there are the other neighbors that, so what happens is, in the yes case, all but one of them are in B, and that one is in A. In the no case, all of them go to B. So I have D neighbors. Either there's one A vertex among them or there's no A vertex among them. I'm going to have to distinguish the two. So the naive algorithm would run this check on all of these D neighbors. You check if it's A or B. So what's the total running time? N times D. And D is the degree of this bipartite graph. And think of it as n to epsilon, or n to the 0.2 for now. I'll tell you why you cannot set it to be so high. But for now, think of it as n to epsilon. So what this would tell you is that the naive algorithm actually takes superlinear in n time to distinguish yes and no distributions.
How do you know whether it lands in A and B? Because like you still need to check whether the vertex on the other side is in A.
Exactly, that's what the naive algorithm does. So you start from A, and you go over all of the D neighbors. Maybe one of them goes to A, the rest go to B. So on all of those neighbors, you run the test of whether it's an A or B. So on all of them, you're going to spend omega n time. And because they're D neighbors, you're going to, in total, spend ND time, which is superlinear.
Yes.
Okay. All right. So this was the first time we actually noticed maybe it's possible to prove a superlinear lower bound. And we thought about it for a little bit. And then we actually noticed that there is a very fast algorithm for this. Yeah.
I have a silly question. The neighbors that are in T,
yeah.
You basically ignore the time, but for each of them, you basically spend constant time?
Yeah, so I'm going to give you the list of all the vertices in T. And you can just quickly check. Yeah, so for those in constant time, you just rule them out. You're only going to have to decide on the remaining D neighbors, whether they're in A or B. Okay, so yeah, so intuitively, it seems that the naive algorithm is the best one can do. So yeah, so we want to see if there's an AA edge or not. Probably have to just check all the neighbors and take superlinear in n time. But there is probably a little bit weird and counterintuitive algorithm that actually solves this instance in order n time.
Singletons identify B?
Singletons.
Right. In linear time, you can use the singletons to find out all of B, right?
No. Singletons are actually also connected to the dummy vertices. So for singletons, if you want to find their neighbors, you're going to have to spend n time. So you can spend n time, and that gives you just one B vertex. So that's not what you can do. Yeah.
Can you see the degrees of the vertex in constant, or do you need to look at the whole list?
So suppose that, yeah, so you can just binary search on the adjacency list. In log n time, you're just given the degree of any vertex that you want. Right. So yeah. So that was actually a great question, because in the yes case and in the no case, the degrees of the A vertices are different. But that's not hard to hide. So you can use similar tricks, as in including stars, or maybe like adding them to B or something. And yeah, so let's not use the degrees. That's a good point. So in the distribution that I mentioned, you can actually use the degrees and distinguish the two very fast. But yeah.
But I still have a silly question. So if you're in the so all neighbors of B are in A, and all neighbors of A with 1 are in B, right? So I don't see why you need to test more than like a constant number of incident edges to be in A to decide which one you're in.
So every A vertex has just one neighbor in A, if any.
Yes.
Either nothing or one. And there are D choices.
Okay, so this is you're essentially you want to find if that edge exists.
Yes. Yeah. So you're gonna have to actually go through it.
Can you, if you just find two vertices in A, with probability 1/n, they'll have an edge between them.
Yes.
So you can figure out in order n time that.
So you're gonna have to sample maybe n pairs, and finding any vertex requires n time itself. So that would aggregate to n squared. So the trick is to use random walks. So this is how you can solve this input distribution order n time. And the reason I want to mention this is because when proving lower bounds, you're going to have to be careful about these kind of silly algorithms. When you design algorithms, random walks that go so long are just rarely useful for matchings. But somehow for this input distribution, we'll see how it can be used. So the random walk algorithm starts with a vertex in A. So we pick a vertex in A. Again, this can be done in order n time. So that's OK. And then what we do is we want to pick a random neighbor in B. OK, among the D neighbors of A in B, I'm going to pick one random and basically random walk on the core vertices. OK, so how long does it take for an A vertex to discover a random neighbor in B? So the degree is n, at most n, actually epsilon n plus d. So it's the degree of this vertex is order n, and d of them go to B. So start querying the adjacency list at random, and in n over d time, you're gonna hit one vertex in B. So just to clarify, I want to make sure that the random walk from A does not step on the dummy vertices. I just want to make sure that it goes to B. Okay? And I'm saying that this one step can be done in n over d time. And then I continue the random walk. So from B, it goes back to A. From A, again, it goes back to B. Because every step takes n over d time, I can afford to do this for ordered these steps.
How do you check whether you're being n? Don't you need to like...
You go over all the neighbors until finding an S vertex, and that takes n time.
Okay.
So I'm not testing if it's a B vertex or A vertex along the random walk. So I'm given the dummy vertex. So once I step on a dummy vertex, I ignore it.
Or you go back.
Yeah, and if I don't step on a dummy vertex, it's got to be a B vertex.
This random walk may visit vertices of A. It's just unlikely, right? This is what's happening.
Yeah. So basically, in the no case, you go from A to B and from B to A. In the yes case, there is a small chance that you actually go through the AA edge. Okay. So if I repeat this for these steps, overall the running time is order n. Every step takes n over d. There are these steps. And if I do this for an even number of steps, say 2d, in the no case, I start from A. Every 2 steps, I go back to A. So I'm definitely going to be in A after these 2d steps. But in the no case, every step that you're in A, there's a probability 1 over d that you actually go through the AA edge. And there's a statistically significant probability that you actually exactly go through an AA edge exactly once. If you have a 2D step random walk. And in this case, if you start from A, you go to B, A, and from A to A, so the parity changes. And because you do this once, you'll end up in actually B. So in the yes case, there's a constant probability that you end up in B. In the no case, you're always going to be in A. And this is enough to distinguish the 2 cases in order n time overall. OK. So the takeaway, yeah.
So how do you figure out you've landed in the top B in this process?
So you're just gonna on the end point of the random walk, you're just gonna run the test if it's A or B, and that takes n time. You're gonna go over all of the. Doesn't matter that you're in the top B or the bottom B. If you're in B, that's definitely going to be a yes case.
So you do a fixed 2D walk and then check.
At the end, you just check what the last vertex.
And it's constant probability. You'll only switch once.
Yeah.
Okay.
Exactly. Right. So this takes order n time overall. And so basically the takeaway is that these long query paths can actually be helpful. Okay, so for some maybe artificial algorithm, but still the lower bound should be careful about these kind of algorithms.
But I guess you also have to be careful about maybe like hitting A 3 times. I mean, like the fact that you hit it exactly once, you're just saying there's a constant probability that
Yeah. So this only works if you go through A exactly once. But there's a constant probability you can repeat this multiple times, and if any one of them does this, then you're gonna for sure know that this is a yes instance. Okay, so
you have to check the first step because
you only check the first and the last vertices of the path, not the vertices in between.
Yeah.
Because otherwise, you have a path of length d. You cannot spend n time per each, or that would be superlinear.
Yeah.
But if you add the edges to make A and B have the same degrees, don't you have, like, you have the same chance of crossing over?
Yeah, that's actually, that's true. And that's also kind of the fix that we have to this distribution. So the fix is as follows. So what was nice about the random walk algorithm? I mean, what was the crucial property that the random walk algorithm used? It was that every time that you're in B, you go back to A. And it's only possible to go back from A to A, not from B to B. Okay. So every time you're in B, you go to A. From A, most likely you go to B, but there's a slight chance that you stay in A. So you want to change this. So in the fixed distribution, we're going to add. So the degrees from A to B is still D. And think of D again as n to epsilon or n to 0.2. And from B to A, we're going to have 1 minus epsilon D edges. So the degrees from B to A is now slightly less. And also, we're going to have epsilon D edges from B to B. Right? So now consider the random walk algorithm. If you're in A, you're still most likely going to B. There's just probability 1 over D that you stay in A. But if you're in B, there's a probability epsilon, relatively large probability that you stay in. So from B, you go to B. Okay. So this is why, so every step, there's a constant probability that you change parity, no matter if you're in the yes case or in the no case. And also, let me just finish the description of the distribution. So in the yes case, we're going to add all edges between A. And just to fix the degree problem, I'm going to also add edges between B, one special matching. So know that all the degrees of the vertices in B and all the degrees in A are going to be D plus 1.
Plus epsilon.
No, D plus 1, exactly. All the vertices in A and B have exactly the same degrees.
Outside the core plus the epsilon n, right?
Yeah, outside the core. Yeah, inside the core. Yeah. Okay. And in the no case, I don't want to have a matching between the A vertices, but this is going to be the matching that I had. Still, the largest matching in this core, in the no case, is just to match S to B. And so the matching is still going to be much smaller. Okay, so this is the fix to the distribution. And this is, in fact, the distribution on which we are able to prove that any algorithm has to spend n to the 1.2 time. How much time do you have?
15 minutes.
15 minutes.
Yeah,
Okay.
between 10 and 15.
Okay. Yeah. So I was a bit slow, I guess, but it's okay. So let's now try to see how we can formalize this lower bound. So there are 4 steps. The first step is this important insight that if you start that any algorithm that you take and queries less than n to the 1.2 entries overall in the whole graph, will not be able to see any cycle in the core. And this n to the 1.2, and just want to emphasize that the degree D here is going to be n to the 0.2. And the reason exactly that we cannot set it to be higher is because we want to get this property that there is no cycle in the core. Okay. So we want to make sure that any algorithm that starts querying the graph cannot see any cycle in the core. Okay. And we get this so long as the number of queries, so long as D is smaller than n to the 0.2. And this is the reason that we get a lower bound n to the 1.2, basically. Okay. And this is also the crucial difficulty in proving any better lower bounds. For example, say you want to even relax the approximation to say 0.999. Can you prove near quadratic lower bound? This is what we don't know how to do. Inside the core, you will see cycles, and you're going to have to handle those. Okay, and the proof of this, you can just convince yourself in 2 minutes if you think about this. So basically, any algorithm, any query results in an edge in the core with probability D over n. Most of them go to the dummy vertices. So in total, we're going to see the probability of seeing an edge in the core for every query is n to the minus 0.8. The total number of edges that we discover in the core is the total queries times the probability that each one lands in core. And that's Q times n to the minus 0.8. Q is n to the 1.2, so this is n to the 0.4 edges. We have n to the 0.4 edges. The total number of pairs of vertices is n to the 0.8. And just for any pair, the probability that it's actually an edge in the core is so small that you can do union bound. It's just all I'm saying is that this is a very simple argument to show that you won't see a cycle inside the core.
So some of the edges that you're adding, for example, from B to B,
yeah,
to make sure that the degrees are the same.
Yeah.
Cannot you? And then you are basically risking closing cycles, and you are proving that you're not. But couldn't you have solved it by, for example, adding edges to T in a more careful way, so that you're like currently you're saying that the vertices in A and B are connected to T in the same.
Yeah.
But you could have created slight discrepancies that will give you the same effect.
So like I want to give away the dummy vertices for free at the beginning. So the degrees to the dummy vertices actually. Oh, so you're saying that for fixing the degrees. Yeah, maybe. But still, we're gonna have to add BB edges because the random walk algorithm. It's important to change the parity even in the no case. Yeah, good point. Okay.
Yeah, just for clarity, can I assume that the queries are deterministic, but then you like shuffle the edges around and
Yeah. So I'm just gonna prove the lower bound for deterministic algorithms now because this is a distributional input, and then you apply Yahoo's min max.
Yeah.
And get the lower bound for randomized algorithms as well. Yeah. So this is I'm basically I've shuffled the edges list, I assume that if you want to query a new neighbor, it's going to be just the next one that you can assume.
Is this exactly the reason why we have 1.2?
Yeah. Okay, so the second step is, okay, now that we don't see any cycle in the core, what we have really is a forest. Actually, technically, we get a stronger bound. It's going to be a rooted forest. Rooted, if you carefully make the edges directed in the order of which vertex queried that edge. But that doesn't matter. So we were going to basically see a tree. And so we start with a vertex. It's going to be either an A vertex or a B vertex. This is hidden from us. And then I'm going to be able to say, OK, so give me a new neighbor of this vertex. Most likely, it's going to be a B vertex. But there's a slight chance it's actually an A vertex. And we won't see these labels. So we keep querying. But how can we learn anything about the graph if we don't see these labels? The only thing that we see is whether we've seen an S vertex, whether we've seen any of those singleton vertices. So basically, I can view the algorithm, any algorithm for sublinear matching in that distribution, as an algorithm that solves this problem on trees. So basically, you have a hidden label on the vertices that determines the probability of transitioning to different types. So from A, you'll always go to B. From B, there's an epsilon probability that you go to B, 1 minus epsilon probability that you go to A. And there's a slight 1 over D chance that you actually go from B to S. So we will see these S vertices, but not the. So basically, this is what the algorithm queries. So once you see an S vertex, you'll for sure know that the neighbor must be a B vertex. So you get some information about the tree, but still there could be multiple realizations of what you've seen. Okay, so the question now is there an efficient process that solves this this problem on trees? And that's what we prove is impossible with less than NT.
Basic question. Can you please again clarify what is the problem you are trying to solve on trees? I can see.
Okay, yeah. Right. So the tree, you have two distributions. The yes distribution, there is a slight chance that from an A vertex you go to an A vertex. There is the no distribution where there's never going to be any AA edge. You never jump from A to A. Okay. So what can we do? So we start with a root. It is either A or B. You don't know. So every time the algorithm can say, OK, reveal a new child for this specific vertex. And it's going to be drawn according to the type of that vertex. The distribution depends on the type of that vertex. So the question is how many times do you have to reveal children to actually distinguish the two distributions from one another? So there's just one slight difference that from A, there is a chance that you go to another A vertex. Okay, good question. So ideally, we want to prove that both in the yes case, so if we want to prove that for any outcome T of this tree, if we prove that the probability that it's drawn from the yes distribution is exactly the same as the probability that's drawn from the no distribution, we're done. We're going to say that, OK, there's no algorithm that can distinguish them. But this is not true, unfortunately. So consider this tree. This vertex has D plus 1 neighbors. And none of them is an S vertex. So this has to be an A vertex. Same for this. This has seen D plus 1 neighbors. None of them is S. So both of these have to be A. You've just found an AA edge. So if you somehow discover this tree, you would immediately get that you're in the yes distribution. So what we're going to argue is that
Sorry, why does it have to be an AA?
this has to be A. This also has to be A because we've queried all of the neighbors and have not seen an S neighbor. B verses have an S neighbor for sure. A verses do not have any S neighbors. So if you see all the neighbors and there's no S between them, it has to be it has to be A. Right. So what we prove at the end is, OK, there are really just small trees that if you happen to see them, they're going to convince you that you're in the yes distribution. But we're going to say that, OK, so for the likely trees that an algorithm discovers, this property is going to be the same. So the probability that you end up with a tree that you can distinguish the two fast is so small that yeah, it's not going to happen. Okay, and so the third step that I think is kind of nice, and sort of to me it feels like the core of the proof is to use correlation decay. So yes, I want to. I don't want to spend too much time on this because I don't have too much time. But basically, so what we prove is morally it's the following: that take a vertex. If you've not queried many vertices close to it, right? So just look at, for example, the radius polylog and below this vertex. If the total number of vertices that you've revealed within that range is not too large, specifically it's smaller than D, okay, you've not basically queried all the neighbors of any vertex that's close to this vertex. What we prove is that the probability that you see this tree is the same no matter what the label of that root is, right? So either you query a lot of vertices close to the vertex, and that's going to give you a lot of information about the label of that vertex. Or if you do not, basically I want to argue that you won't know anything about the label of that vertex. Okay, so this can be formalized a little bit. Yes, this can be stated a little bit more formally, but morally what we basically say is that either you make a lot of queries close to a vertex, or else you won't know anything about the label of the vertex. Okay, so it's going to be A or B, and you won't know anything about it. And this holds even if you condition on things above the vertex, but I'm not going to talk about that. Okay. So how is this useful? So using this correlation decay lemma, and we prove this via correlation decay, we get that if you have an AA edge UV that the algorithm queries at some point, the algorithm will see AA edges. That's inevitable. We're going to have to prove that the algorithm won't notice that this was an AA edge. So how do we argue this? We say that so if the total number of queries close to one endpoint of this AA edge is much smaller than D, right? So we have not made a lot of queries close to at least one of the endpoints of this AA edge. So from the perspective of the algorithm, this is the algorithm won't know that this is an A vertex, right? So basically, even knowing that one endpoint is A, so basically we have this AA edge. So suppose that I even tell you that this is an A vertex. If you've queried a small number of vertices around this other vertex, you will most likely think that this is a B vertex because you know this is A. Most A vertices, most of the neighbors of A go to B, and this won't give you any information, any indication that this is an A vertex. So from the perspective of the algorithm, you think that actually this is most likely you think this is an AB edge. So the algorithm won't know where to concentrate the queries. So a lot of the queries will be wasted, and you won't be able to essentially prove there won't be an AA edge where you've queried a lot of vertices close to both endpoints. Okay, so that's I guess as far as I can go. Okay, just so I'm going to skip this part. So we have a follow-up work that proves a new lower bound for 1-epsilon approximations for low-degree graphs. Yeah, I'm not going to talk about this, but basically just to conclude. These are the algorithms we know for the sublinear matching problem. These are the lower bounds. There are a lot of nice questions. Two of my favorites are, can we get better than half approximation still in order and polylog in time? And the second one is, for 1-epsilon approximations, can we achieve an algorithm running in n to the 1.99 time? So this algorithm, it runs in n to the 2 minus epsilon time, where this epsilon depends on the approximation. I'm asking is it possible to get rid of this epsilon in the exponent? Maybe you can multiply one exponential in 1 over epsilon to n to 1.99. Yeah, such an algorithm would be really cool. Okay, I'm going to conclude the talk now.
So we have time for one quick question. Maybe Julian, you can walk up and have already. One quick question.
So I'm not sure if I understood correctly, but this tree model technique, doesn't that sound very, very general? Right? I have the feeling it didn't have anything to do with matching then anymore. And as soon as you can
Yeah,
frame,
it's all about the distribution, exactly. Yeah.
Yeah.
So you just specify what the tree model, what the distribution
Yeah.
of going from A to B and from B to A is, and that comes from the construction for matchings. The rest of it is just not. It's just
okay.
about the tree
So
model.
this could potentially be a very general tool for similar
I think so.
artworks. Thanks, cool.
Thank you again. Yeah, and now we have one of our co-organizers give a talk. Julian Schun from MIT is an assistant professor at MIT, and he'll tell us about the parallel batch dynamic K-chord decomposition.
Okay, great. Thanks a lot. So I'm a bit under the weather. I'm going to keep my mask on. If anyone wants to put on their mask or leave, I won't be offended. Okay, so today I'm going to talk about our work on parallel batch dynamic K-chord decomposition. This is joint work with Quan Liu, Jessica Shi, Xiangdi Yu, and Lakshman Duapala. You've heard a little bit about this work in Quan's talk earlier in this workshop, but I'll provide some more details.